Now let's take a look at the motor system in your brain. There's three major types. We're going to start out with skeletal muscle movement. That's known as the somatic motor division. Then we have neuroendocrine signals that will be mostly directed through the hypothalamus and also pituitary, and then adrenal medulla is part of the neuroendocrine pathways here too. And then the visceral responses, they are under the control of the autonomic nervous system, so it'll be sympathetic and parasympathetic regulation of smooth muscle in that case. We have voluntary movements. They're from the primary motor cortex, so this would be also these association areas where you have that slice of cortex that's associated with the somatic motor evaluations. So here's a brief overview over how the brain functions in controlling your behavioral states. The brain in general is a modulator of sensory and cognitive processes. Let's skip down here to the reticular activating system. That system basically wakes you up in the morning. So the RAS, or reticular activating system, controls consciousness, and it's what's waking you up in the morning and starting your day. Now let's take a look at some major neural networks and pathways that you find in the brain. Let's start here with the noradrenergic network of neurons. They operate with the neurotransmitter norepinephrine, and you can see in blue there are some arrows here, sort of roughly the pathways. You don't have to memorize this, but you should know norepinephrine is associated, these pathways are associated with attention, sleep-wake cycles, learning, memory. So these are the pathways that in kids with, or in people with attention deficit disorder, they seem to be not working properly, and so people with ADHD or ADD, they get these medications that will enhance the norepinephrine pathways or this noradrenergic system to enhance learning and memory. Here will be the serotonergic pathways. You can see, so serotonin is commonly referred to as your happy neurotransmitter. It's involved with emotions, of course, and how you feel about yourself and the environment that you're in. These pathways operate with the neurotransmitter serotonin, and major functions here include mood and emotional behaviors, and that's very commonly associated with the neurotransmitter serotonin. Next up are the dopaminergic pathways, using the neurotransmitter dopamine, and there you have, of course, the substantia nigra is a big part of these dopaminergic pathways, where you have then a motor control, and very importantly also the your reward center. This can be very problematic because if you are using substances that are releasing dopamine that signals to your brain reward and makes you feel good, then you have a tendency to come back for more, and you have to be careful about substances that release dopamine because they're very addictive, and you just have this drive of wanting more of that substance. Finally, here the cholinergic pathways. These pathways, you can see in red, they're pretty much going all over the place, using acetylcholine as the neurotransmitter, and you can read some of the functions about sleep-wake cycles, learning, memory, sensory information. So anyway, I'm not a big fan of these rather small images, but you can just take a look at it. You do not need to know specifics about these major neural pathways and the neurotransmitters that they need. We will be picking up several of these in other lectures. Here is an image, probably an MRI image of brain activity as it's going through the brain, measured here sort of in yellow and red, higher activity centers, and blue and green would be lower activity. Now, the overall measurement of electric activity in the brain is done with an EEG, an electroencephalograph, and it's recording overall electric activity, no specific areas. It wouldn't be pinpointing, let's say that, oh, in this area over here we have high activity. It would just be an overall electric activity that's going through the brain. And you will record that sort of at these surface electrodes. Hopefully you got a chance to take a look at that in the lab section. There was some videos posted about EEG recording and what these waves mean. Here's an EEG recording that shows you the onset of a seizure in a person right here. So normal brain waves before, and then massive electric activity as somebody's experiencing a seizure. Seizures are also referred to as sort of lightning storms in the brain. You'd see massive electric activity. Now, as far as the main brain waves that you see in an EEG recording, what you need to know are these four: alpha, beta, theta, and delta waves. Let's maybe start with the delta waves. Delta for deep sleep waves. So these are high amplitude, so it means they're tall waves, high amplitude, but low frequency waves. So you have very few cycles here going through. So these are deep sleep waves. Now going back up here to alpha waves, and if you did the lab on this and watched the videos, you already know this. Alpha waves have relatively low amplitude, so they're kind of small waves, and they're sort of not too high in the frequency either. So this would be characteristic of an adult that's his eyes closed, kind of in a drowsy state, maybe barely awake. Let's picture yourself in a boring lecture, you're almost asleep. Your brain waves would show alpha waves. Now, if you find a lecture stimulating, or you're looking at something or reading something, there's visual processing going on, you're learning something, then you would show beta waves. Now, beta waves aren't taller than the alpha waves, so the amplitude isn't any higher than the alpha waves, but the frequency, take a look at that. So you have a lot more cycles per second going through the brain, and that indicates much higher activity. Theta waves, they're kind of erratic, and there's different theories about that. Some people say these are associated with emotional distress. Some others say that they're also associated with sort of hypnagogic imagery. If you're daydreaming about something, or you're imagining something, then that would be more sort of a creative kind of brain activity that's associated with theta waves. And here are the EEG patterns in writing. So the alpha waves are typical of a person that's awake but eyes closed, very relaxed, almost sort of falling asleep. Beta waves, high activity, you're stimulated, high mental activity and processing. Theta waves, well, there's slightly different takes on those brain waves. Could be also associated with emotional distress, or somebody daydreaming, imagining something. They seem to be fairly common in newborns. And delta waves, those are your deep sleep waves. They have very high amplitude but very low frequency. Let's take a look at what these brain waves might look like in a person that is going through various stages of sleep. So awake brain waves are shown up here, so pretty high frequency right there, high activity. And then here somebody's going into the various stages of sleep. REM, just for reference, that is your dream phase. So REM stands for rapid eye movement. And it's pretty high activity when you're taking a look at that, when somebody is asleep but dreaming, so almost awake. Here are the different stages, and you can see how the waves get taller, but the amplitude gets higher as somebody goes deeper and deeper into sleep, but the frequency of the waves gets smaller. And here, same thing, one more time. So if you're awake, eyes closed, you showed this alpha pattern of brain waves, and then you're going into REMs. REMs is this is your rapid eye movement sleep. That would be your dream stage. And as you're going deeper and deeper into sleep, here you can see really, really tall waves, and stage 4, the deep sleep waves, low frequency but very high amplitude. And here you can take a look at the different stages of sleep. As somebody's falling asleep, they're going very rapidly down all the way to the deep sleep stage, and then we're going through cycles as we sleep. Takes about an hour or so to go through one full cycle of going all the way down to deep sleep stage 4, And then coming back up, here will be an REM, your first REM stage. You're going back down into deep sleep, and then you're going back up into an REM stage. And then as you're approaching the morning, you don't go all the way back down into deep sleep, but you're staying sort of more in this stage 2, going back up into dream phases. And hopefully you got 7 or 8 hours, ideally. In your book, you'll find this particular figure right here, very similar to the previous one. Just take a note that you only approach or you will only go into the deep sleep, stage 4 sleep, in the beginning of your night, so about the first 3 hours. Now here are more brain functions. So let's take a look at motivation. Now, without motivation, nothing works. So motivation is everything. It's the drive for you to do anything. And so we define motivation also as drives that give you, that motivate you to do certain things. And they work together with autonomic and endocrine responses. Motivated behaviors stop when a person has reached a certain level of satiety. So this refers to eating. So we're all addicted to 2 things as humans. We're addicted to food and to sex. That's just sort of, that's how we're wired. Our brain is wired like that. We're always motivated to seek out things that ensure survival of us as an individual and survival of the species. Now, you can hijack the motivation system, and there will be drugs, and we'll talk about that in another place. Brain function moods. So they're similar to emotions, but longer lasting. There are many mood disorders these days. The biggest one being depression, and many people afflicted of that. Basically, depression is a mood disorder, and it leads to sleep and appetite disturbances, all sorts of, basically people feel just down the whole time, and they are not motivated to do anything. Mood disorders, or in this case depression, is treated with antidepressants, and antidepressants, by and large, they will be serotonin specific reuptake inhibitors, meaning that you want the happy neurotransmitter serotonin to be around longer. Now here's another big function of your brain, and that's learning and memory. This would be definitely worth a whole course. I don't know if you've taken a psychology class. There they're talking a lot about associative learning, non-associative learning, memory types, how you go from short-term to long-term memory. We don't really have time for this, but so there's this long-term potentiation of neurons and how synaptic networks are working. Again, we really don't have time to cover a whole lot of this, but here's sort of a brief overview of how memory processing works and how you're consolidating short-term memory into long-term memory. And the key is, well, you should know this as students, the best way to learn is repetition, right? So the 3 main ways of learning something will be: number 1, repetition; number 2, repetition; and number 3, repetition. You guessed it. Now I want to finish up this lecture with taking a look at language. Mainly these 2 association areas, Broca's area and Wernicke's area. Broca's area is involved in the articulation of speech. So if you want to say something, then you need to give directions to the muscles in your tongue and vocal cords and everything, so to get the language out. If somebody has damage to Broca's area, then they have slow or poor articulated speech. They may be stuttering, and that will be something indicating Broca's area damage. Wernicke's area damage means that you don't understand what somebody has said. So language comprehension is lacking. And that would mean that that's a much bigger problem, of course. Somebody with Wernicke's area damage might have very rapid speech, but has no meaning to it. Now here's how you process a written text. So you read the word, and then the visual input goes into the visual cortex for evaluation. Then you use Wernicke's area to understand what you read, and then Broca's area to get the words out, including using your motor cortex, of course. When you hear something, use your ears the auditory cortex, then Wernicke's area, then Broca's